Hello friends, let us begin our special lecture session on the topic of Boolean Algebra. This is a prerequisite session for the chapter of Mathematical Reasoning or Mathematical Logic. It can also be used in the chapters like set theory or probability theory. We will mainly focus on the preliminary concept of Boolean algebra here, and will learn how to design a truth table using the concepts of Boolean algebra, as truth table will be largely used for our logical discussion in the chapter of mathematical logic. Okay, so here you can see the inventor of Boolean algebra was George Boole, who in 1847 AD, in his first written book, The Mathematical Analysis of Logic, discussed that Boolean algebra is a branch of algebra which deals mainly with truth values of variables. Mainly, it deals with the truth values of the statements and tells us that either a statement is true or false. Okay. It finds many applications in the areas of digital electronics, set theory, probability theory, VLSI technologies, and many more. Okay, so it is a widely used tool and a widely used application of the branch of algebra. Okay, in 1930 AD, Claude Shannon, in his switching circuit theory, said that circuits can be designed using the ideas of Boolean algebra, or using the ideas given by George Boole in his Mathematical Analysis of Logic. Okay, so let's now see how we can use the concept of Boolean algebra to form a truth table. Okay, as we have already stated that Boolean algebra deals with the truth values of statements. You will find more about the definition of statement and different type of sentences in the upcoming lecture of mathematical reasoning or mathematical logic. But let us now take some example to understand the formation of truth table first. Let's say we denote our statement by these letters P and Q. Say P is a statement. Let us take any statement such as today is a sunny day. Let us take another statement Q as the wind is blowing very fast. Okay, so these are two statements denoted as P and Q. P says today is a sunny day, and the statement Q states that the wind is blowing very fast. Okay, so any statement, we can see that it has two values. Either it can be true or it can be false. The statement Q also has two values. Either it can be true or it can be false. Okay, so if we try to gather these values in the form of a table or in a tabular form, then what we will get? Say P and Q. So P can be true and Q can also be true. Okay, P can be true and Q can be false. This is also a possibility. P can be false, Q can be true. And again, P can be false and Q can also be false. Okay, so there are 4 possibilities of P and Q to be true or false. And here we have formed the truth table for P and Q statements. Okay. This type of statements you will see in your later course, that this type of statements are known as simple statement. Okay, simple statement or atomic statement. And when 2 statements are connected together with the help of some logical connectives, they are known as compound statements. You may be already familiar with the term of conjunction, as you have seen that term in your English course. So we have some logical connectives, like this connective is known as the AND connective. Okay, this is known as OR connective. This is known as NOT connective. AND is also known as conjunction. OR is known as disjunction. And NOT is known as negation. Okay, so these are the type of connectives we generally use to form the compound statements. There are some more types of connectives, like this one is known as implication. It is used with the statement of if then, and this connective is known as double implication. Okay, this is used in case of if and only if. So these are the connectives we generally use to form our compound statements. So we can use the AND connective to form a compound statement using P and Q. So we can write P and Q can be written as today is a sunny day. Today is a sunny day and the wind is blowing very fast. Okay, so it is an example of a conjunction statement where we have used the AND connective to connect 2 simple statements together. Okay, if we see in the truth table that what are the truth values for P and Q, we see that the AND connective gives us the true value when both of the statements are true. That means when P and Q both have true values in them, then only the AND connective gives us true value. That is, in this case, the first one is true for us and all the rest of others are false. Okay, so this is the truth table for the AND connective. Okay, similarly we can form a truth table for the OR connective. Let's say we form the statement for OR. So it will be written as today is a sunny day, or the wind is blowing very fast. Okay, so the truth values of OR connective or P or Q statement are those values which are either true in any of the statements. That is, if we have true value in either of P or Q, then our statement is true. So here we have both of them as true, so P or Q must be true. Here we have P as true. Q can be anything, either true or false. We will get the value as true. Next we find that P is false. So Q have to be true to get this result as true. And if P is false, then we check for Q and Q is also false. Both of the statements are false. Then we get P or Q as false. Okay. So this is the table for the OR value. Okay. That is P or Q. So we can form different truth tables with different logical connectives. The not value or the negation gives us the opposite of any statement. That is, say P can be either true or false. Okay. Then not P, where there is true value for P, not P will give us false. And where there is false value for P, not P will give us true. So in this way we can form various truth tables to find our results. As we have discussed earlier, in Boolean algebra we represent the truth values with the help of the numbers 1 and 0 also. That is, the true value is denoted by 1 and the false value is denoted by 0. True is denoted by 1 and false is denoted by 0. Okay. So let us take three statements P, Q and R and let us plot its truth table. Okay. So this is the truth table for the three statements P, Q and R. As you can see here, we have denoted true values as 1 and false values as 0. And we can see that in the first row, all the three statements give us true value. In the next statement, when P is true and Q is true, but R is false. In the third statement, P is true, Q is false, but R is true. In the next statement, P is true, Q is false and R is also false. In this way, we can find different values for P, Q and R. And these are the list of all possible truth values for the statements P, Q and R. One thing you must notice here is that in the previous example we saw that we have two statements and we had 4 rows there. That is true, 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 false, false, true and false, false. Here we have 3 statements and we have 8 rows here. And I am saying that these are the maximum possible rows which gives us the truth value for this or these statements. So how can I find that how many rows will be there if the number of statement is say n, or if the number of statements is in general terms, can be anything. In that case, we use the formula 2 to the power n to find the number of rows of the truth table. Okay. As you can see here, here are 2 statements P and Q. So the number of rows will be 2 to the power 2, that is 2 square or 4. So here are 4 rows. Here are 3 statements. So the number of rows are 2 cubed, that is 8. Okay. So in this way we can find out the number of rows present in a truth table. Okay. So here you can see that the truth table of PQR is already given here. Let us perform some operations on these statements and get our understanding clear over the concept of using logical connectives in the truth tables. Okay. Okay. So here we are going to perform these operations on the statements P, Q and R. Let's see what happens. So when we are performing the task of not P, so what will be the rows in this column? Let us see those. So the rows we got in not P are 0, 0, 0, 0, 1, 1, 1, 1. That is the negation of operation performed over the statement P. Not of 1 gives us 0 and not of 0 gives us 1. Similarly, we can also find out the results for the column of not Q and not R using the columns Q and R. So you can see here that these are the rows obtained for the columns of not Q and not R using the columns Q and R. That is, the negation of Q gives us not Q and the negation of R gives us not R. Next, we will perform the OR operation over P and Q, and finally we will negate the statement. Okay? So P or Q gives us 1 here. As both of them are 1, we will get a 1 here. And then we will perform not of 1, which will give us 0. Okay? Next, for this statement also, we get a 0. For this, we get a 0 again, as P or Q is 1. So, not of 1 is again 0. Next, here also we get 0. In this statement, we get a 0. Here we get a 0. Here we get a 1. And here also we get a 1. Similarly, we will perform this operation on the columns of Q and R, and then we will negate the statement. So after performing the operations on the columns Q and R and negating them, we have found that these are the results. Okay? We will now perform the AND operation over the columns not P and not Q. Okay? So on performing the AND operation over these two columns, we find that, so on performing AND operations over the columns not P and not Q, and then on the columns not Q and not R, we find these two columns. Okay? We can clearly see from here that this column, not of P or Q, gives us the same result as not P and not Q. Similarly, not of Q and R, not of Q or R gives us the same result as not Q and not R. Okay? So, we can see that these two results are same and these two results are also same. And these are the part of famous law known as the De Morgan's law, which you will study later on in the chapter of mathematical logic. You might have also seen this law in the chapter of set theory. Okay? So these are the De Morgan's laws. That is, not of P or Q gives us not P and not Q, and not of Q or R gives us not Q and not R. Okay? So we have found the results for the De Morgan's law using our truth table for three statements P, Q and R. Okay? These are some of the diagrammatic representations of the logical connectives. So we are representing the connectives AND, OR and NOT using logic gates and using Venn diagram here. Okay? So the logic gates are very much useful in forming the digital logic circuits, which you will use later on in your higher studies. Okay? In circuit theory and in modern physics also, these logic gates find many applications. So this is the logic gate for AND connective. Let's say we have a 1 passing through both the channels in this logic gates. then P and Q will give us output as 1. Okay? If say any of them is switched to 0, then 0 and 1 will give us 0 here. And if both of them are 0, then also we will get a 0 here. So the logic gate AND performs in this way. Okay? Similarly, we can see the functioning of logic gate for OR. So I am not going into the deeper concept of logic gates in this chapter because this is out of the scope of our current study. There are many more logic gates like the XOR gate, XNOR gate, and the combination of different logic gates using AND or NOT gate. Okay? They can be NAND gates also. The NAND gates are the combination of NOT and AND gates. Okay? So there can be many more logic gates, but we are not covering that topic here. Next comes the representation of the logical connectives using the Venn diagrams. So here are the main three logical connectives, that is AND, OR and NOT. You can see the representation here is given for the AND. This is actually P and Q. Okay? This is the intersection part which is common to both P and Q. So that is the part for P and Q, AND operation. This is the representation for the OR part, that is P or Q. P or Q. Okay, that is, it is the union of both the sets in terms of set theory. And this is the operation for the NOT. Okay, you can see the Venn diagram here that this is a universal set in which the set of P is present, and NOT P covers all the areas other than that of P. Okay, so this is the representation of NOT connective. So in this way we can represent the logical connectives using logic gates and Venn diagrams. So this was a precise concept on the chapter of Boolean Algebra, which you will find helpful for the chapter of mathematical logic, set theory, probability theory, and many more areas. Okay? This session is mainly for those students who are not aware of forming a truth table or logic gates or Venn diagrams. You may see this chapter of Boolean Algebra in your class 11-12 computer science syllabus also, those who are taking that subject as their main paper. Okay? So I think this session will prove to be a very helpful session for you all. Thank you for watching. Meet you in the next session.